recording today's presentation, right? So we're now talking about radioactivity. Let's see if I can minimize that, okay? So we're talking about radioactivity, and last class we were talking about how important this is. And something that I want to do after I go about this for 20 minutes or so, I want to sit around and talk about the different possibilities that you as a science major have for the future, because it's really interesting. As we mentioned before, radioactivity, for instance, can be used in medicine in many ways. For instance, if you are going to be labeling reactions in the organisms, I mentioned iodine 131, for instance, as one of the elements that we use in medicine a lot that are radioactive and so on. And just the use of nuclear radiation as a way to treat cancer and so on, because one of the things that we have to know is that the radiation emitted by the nucleus is highly ionizing. So this ionizing property, which means that when you have one of these particles going through, let's say that this is one of the particles going in that direction, or one of the radiations there, and you have an atom with the electrons around it, it can knock off some of the electrons, and then it will make this atom an ion, and then the behavior of the atom as ion in the organism is going to be different, right? So one of the things that can happen, for instance, is that radiation may cause cancer, right? So you have to be careful with that and so on. We mentioned how radiation in different ways, like X-ray radiation, that is not nuclear radiation, has to be protected. When you go to the dentist, you want to have an X-ray, you are covered the rest of your body with lead, right? Because lead is a heavy element, compound, that can protect from radiation. So last class we talked about, well, what is radioactivity? And the first thing we have to remember is that we are talking about a nuclear reaction. It's something that is happening in the nucleus, right? So this has two branches in our analysis that we have to take into account. If the properties of the element are given by the electrons, then changes in the nucleus will affect how many electrons do we have around, because if the nucleus is losing protons, for instance, the positive nature of the nucleus, let's say that I have all these protons here, and somehow some of these protons are breaking off like an alpha particle. Remember that we mentioned that an alpha particle will have 2 protons and a mass of 4, which means it has 2 protons and 2 neutrons. Therefore, this is going to be a new nuclei. So the new nuclei will be now behaving as a different element. So we'll see some of that in a few slides. So we also mentioned that one of the beauties about scientific research, or just research in general, right, is that whenever you face an obstacle, there is this challenge of how do you go around or above that obstacle to find a solution, right? And I mentioned how if you have a bunch of radioactive atoms, you do not know which one of those atoms is going to decay. But one thing that you can say is that the more you have, the probability, the likelihood of one of these atoms to decay is going to increase. So you can write an equation where you say that the rate of the reaction, this would be the rate of the reaction, when you have how many nuclei are changing in time. So you have, this would be, N would be the number of nuclei, right? And this would be, of course, the time. So you have time here. So the rate of the reaction, how many are you losing, will be proportional to the number of nuclei that you have. And the way of fixing this proportionality as an equation is to include a constant of proportionality that in this case I am just calling lambda, right? So the rate of the reaction is proportional to the concentration here, to the abundance of the nuclei. And this we will call in chemistry in general a first order reaction, where the rate of the reaction depends linearly with the number of atoms that you have of that particular compound. And of course, if we use calculus here, you can rewrite this equation by using the differential of n over t. And if you have an equation like this, could be like the big delta or the small delta here, you can solve that equation by saying that the number of the nuclei at any particular time is going to be an exponential function. This would be the solution for this equation, right? And last Monday, last class, no, it was Friday, we introduced the idea of a time that we call the half-life, which is the time it takes for a particular amount to be half the initial amount. So in this case, that the number of nuclei that I have after one half-life is going to be 1/2 of the initial amount, right? So these are terms that we will use when we're talking about reaction rates. How long does it take to produce a particular amount, and you can then define that as a particular time, right? It could be critical, or it could be saturation point, or whatever. You can call it in many different ways, right? This plot over here gives us an idea of how the number of atoms that I have at that particular time change with time. So we see here, for instance, that if I start with a particular amount here that I will call L0 or N0, then if I move here to when I have half the amount, which will be this point over here, that would be what we call the half-life that I am saying T 1/2, right? And if you go another half-life, then you get half of that amount, right? That would be 25% of the initial amount, right? That's how we're calculating this. And if you wait another half-life, then you have half of that, that would be 1/8 of the initial amount. And then 1/16, 1/32, 1/64, and so on. You're going to be just divided by half every time, and so on, forever, right? So this is a better plot here of something similar to what we're going to be doing in the lab at Reed College, and also here we're going to be looking at measuring the half-life. So for instance, radon-220, you probably have heard of radon as a gas that is mainly in basements and so on, and it's a byproduct or product of the decay of the uranium chain. And radon is then a naturally produced radioactive element, and the half-life here would be about 1 minute. So you see that, for instance, if you have your basement open or whatever, then the radium can just escape because it's a gas. But even if you just leave it closed without any new radium getting into the basement, it will decay eventually, right? So this one here, the 220, has a 1 minute half-life, and we see here that, for instance, if we start with 1 million atoms, let's say, right? Then after 1 minute, you have 500,000, right? After another minute, then you have half of 500,000, that would be 250,000, and so on. So every minute here, you have half of the original, half of what you had before, and so on, right? And the plot here is not very well done because it looks like you eventually get to zero, but you will never get to zero, right? This is never, it approximates to zero, but it's never zero. You always have half the initial amount, right? So that's an important concept here. And of course, yes, ma'am.
What if your two samples, or what if you took two samples and added them together, but they were created at different times? Are they going to?
Good question. What it counts is how much do you have at that particular moment. It doesn't matter what the history of those were before. So if you have this 500,000, for instance, that started like 2 million, or they started like 1 million, that's the nice thing about this statistical model, is that it doesn't take into account the history behind. Now, the question is also important because if you do know what the initial amount was, you can measure the time it passed. That's how we use carbon-14, for instance, to date things in historical, I mentioned that in archaeology, right? In archaeology, if you want to know how old a ruin is, you can use, if we know how much you had at the beginning, let's say that you know that you have 1 million, and then you measure that today you have this amount here, right? Then you can extrapolate this and say, oh, okay, if I had 1 million, that was 4 seconds ago, right? You can go back. And that's a big, in many cases, when you're dealing with radioactive dating, that's one of the main problems, is that sometimes it's difficult to know what was the initial amount. I used to do potassium argon dating, and the question is the initial sample does not have any argon-40 to start with, and if there is some initial argon, then you're in trouble, right? So we have to be able to distinguish the initial argon from the one that you are measuring here, and so on. So that's a good question. So it doesn't matter where these atoms came from. Once you get them here, then you know that they will follow the same law as all of the atoms of that particular time. So this is an interesting question, because when I am talking about this equation, this lambda is going to be characteristic of that particular radiation, right? So you might have a radioactive isotope that has different kinds of radiation, and then each one will have its own lambda, right? That's the case of potassium 40, for instance. Okay, so that would be how we have the half-life there. So let us just remember what we mentioned about the different kinds of radiations that we can have there, or symbols. Like, for instance, if we have the proton that is positive, we'll use a big plus here for the proton. The neutron, remember, has no charge, so you can put a 0 charge there. Now, if you are going to be using the symbols that we have been using before for an element, where you have the element given by the atomic number 8 here, and then you have the total mass of the element over here, then you can use this notation over here, where you say the neutron has no charge and has a mass of 1. Right, so that would be one way of noting it. The electron in this case here has, let me get rid of that. The electron here has a negative charge of 1 and hardly any mass, so you would say zero mass, right? The alpha particle that we mentioned before is very similar to the helium nucleus because it has 2 protons and a mass of 4. So it has 2 protons and 2 neutrons, so the mass of 4. So the helium symbol is often used for the alpha particle. And Caleb, you asked about the question, is that a helium nuclei or like an beta particle, like an electron and so on? That's a very, very good question. For us, you can say that it is, right? Because if it looks like Caleb, is named Caleb, sits where Caleb sits, has Caleb's friends, is Caleb, right? That's how we're going to say it, right? You can never be sure, because that's the nature of science, is that you can always find something that is a little bit different. But in our case, we can very safely say that the beta particle is like an electron. Yes?
Does an alpha particle, when it's emitted, carry electrons with it?
No.
Okay, so
That's a good question. No. You are thinking about a positive, this is an ionizing a positive charge of 2, but then if it finds some electrons around, it can change into an alpha. And that's how we have a lot of the helium that we have in our in nature. It was originally made as alpha particles. And then they acquire electrons along the way, and it becomes helium gas. And so helium, if people are getting helium from the ground, is normally related to some radioactive process. And so on. So that's a very good question. So all of this, when you, they are like, they will have a particular charge, right? Well, not all of them. If you're talking about a neutron, has no charge, right? And then you have the other case, like for instance in this case, what if you have something that has only the positive charge, but no mass? So very similar to the beta particle that has a -1, but in this case, it has a +1 charge, right? And then the question is, where did that come from, right? So we're talking about new particle, right? So imagine that you have a proton that has, like in the case of the hydrogen ion here, right? You have only one proton. Well, what if that proton gets rid of the positive charge without losing mass? Well, that would be like a neutron, right? Because neutrons have the mass very similar to protons but have no charge. So when you have a reaction where the positron is emitted, what is going to happen to your atomic number here is that it's going to decrease by 1, right? So let's say that you have an element that is like 19, for instance, and emits a positron here, right? So it's emitting that, then the element that is going to be left is going to be 18, right? Because this beta mass will have a +1. So this is going to be +1 here, and 18, that gives you 19 in electronic. So that's how we are going to be looking at the reactions, right? So this would be kind of a summary of what we're talking about when you are dealing with only the nucleus. We call that the nuclei, right? And that nuclei there will have very specific characteristics. And normally what you will be doing is using the same notation as we use for the elements, where you have the number of protons, that in this case we were using the letter Z for the atomic number, and the letter A for the atomic mass, right? So that would be A would be equal to C plus the number of neutrons, right? So that would be an equation that we have to remember. So if we have a reaction like this one here, for instance, where uranium-238, for instance, is losing or is giving up an alpha particle that is 2 protons and a mass of 4, then whatever is left will have 2 protons less and 4 masses less. So the product would be 90. If you have 92 minus 2, that's 90. You look in the periodic table, what is the element number 90, and you find the thorium. So then you put thorium there as the daughter nuclei, and then the mass of that thorium would be 238. That would be 238 minus 4, right? Because this 4 is coming from what is leaving from the helium. So the daughter would be 234. So this is the mass of the thorium isotope that you are leaving there, right? Very simple sum and subtraction, right? Depends on what you are doing, right? So that's the thing. So The sum of the masses gives you 238, so the sum of the mass numbers in the product here would be 238. The sum of the atomic number, 92, will give you the same number as you have in the product, right? So products and reactants will have to add up, right? Now, something that we're going to be looking at next Friday is if you have, let's say in the case of helium, you have 2 protons and 2 neutrons. You would expect that the mass of that helium is going to be the sum of the masses of the 2 protons plus the 2 neutrons, right? But when you actually measure that, you find out that they are very close but not exactly the same. Because as with any reaction, when you put things together, there is an energy change, right? And that change is what happens when you have a nuclear reaction, is that there is energy always coming out, right? So one of the other radiation that we see coming out from nuclear reactions are gamma rays that we see here, right? The gamma rays, right? So that's that's electromagnetic radiation that carries no mass and no charge, just energy, and it's kind of powerful. It's also ionizing, and it can go through a lot of material. So that's another kind of radioactive radiation that you get. So you have the alpha, the betas, the gammas, the positrons. You can also have other kinds of reaction, like for instance, you might have what we call electron capture. In some more physics text, you will call this the K capture, as K being the first layer of electrons. So let's say that you have a nucleus here, and remember you have the electrons flying around the nucleus, right? It might happen in some cases, like for instance in potassium-40, that once in a while you have that one of these electrons is trapped by the nucleus, absorb that electron, right? That's what we call electron capture. So how are we going to be looking here at the chemical equation or the nuclear equation? Well, if you have so many protons here, which are positive, and now you add one electron, the protons are going to be cancelled by that. One proton is going to be cancelled by that electron, right? So if you have, let's say, 19 protons, and then you have one electron, minus one, that means that you are going to end up with 18 protons in the new nuclei, right? And because you have less protons, then your element is going to be rearranged. And if you lost or you use one of the electrons to be captured, then the number of electrons around the atom are going to be equilibrated by the number of protons that you have there. So you just have a new element, right? In the case of potassium, I believe is calcium. So the other thing that I would like to say here is the power that different rays, nuclear rays, have. And this is not only based on what kind of charge do you have, but also on the size and mass of the radiation. The one that you can stop easy, which in some cases is the most damaging, would be the alpha particle. If you have a very thin layer of lead, let's say about 0.01 millimeter, very thin, like a paper-thin layer of lead, you can stop the alpha particles. So even clothing can stop alpha particles. But if you get alpha particles in your skin, they do a lot of damage because they are very heavy and very highly ionizing. Very small penetration with high damage, right? And then you have the beta particles that have more penetration than the alpha particles, but not a lot of penetration. If you have about 1 millimeter lead layer, you can stop the beta particles. And in fact, we have, and we're just purchasing a new source for alpha to do this experiment. That's one of the things that we might do here in class, because I have a detector here, And if we put the source there, we can just play with paper and aluminum or lead and so on, and see how far they go looking at that. Right? So that's kind of a simple experiment that we can do.
How does a particle without mass cause damage? How does a particle without mass cause damage?
Well, the thing is that because of the alpha particle, they have the high charge as well. So they have two positive charge. So that would be, and it has to do with the amount of energy that you have, the momentum of the particle. The bigger, the more momentum, the more energy you have, and that energy is going to be transferred into the atom that is being ionized.
So since it has energy, according to Einstein, would it also then technically have a mass?
Yes. Yes.
But we're saying that it doesn't have a mass.
No, alpha particles have a mass. Beta particles.
Beta particles.
Yeah, they have very little mass, negligible.
Okay.
They are about 2,000 of a neutron.
Okay.
Yes. And they have a negative charge, right? Or positive, you're talking about a positive, right? So get it. So what we have here then is an idea of how these reactions happen, right? You have a unstable nucleus that somehow get rid of that instability by emitting, in this case, an alpha particle. So here we have the alpha particle being emitted here, and that's how we have the model for radioactive decay, right? And so this would be the example for beta decay, and so you have radium-228, for instance, decay by beta here. So of course the number goes from 88 to 89, and that will get then the actinium nuclei, right? And because of the electron that is emitted here has no mass, then the total mass of the actinium will be the same as the radium that is emitted there, right? So that would be the equation for beta, right? So all these equations would be basically the same. Now, the gamma emission has no mass, so that would not change what you have. So for instance, let's say that we have the uranium-238 that decays into the thorium-234 that we saw just before, and the helium, but some of the energy is also emitted as a gamma. But the gamma has no mass and no charge, so it will not count in our equation here for calculating what is the product. We have to know that it's only those that have the charge and the mass that are going to be used in our calculations there, right? So you might have a situation where, let's say that you have here the radioactive atom that decays into a daughter that is also kind of unstable. But this instability can be released by emitting a gamma ray, and then you have the daughter that is stable. So sometimes you might have a delay, very brief time, between the formation of the daughter and the release of the gamma ray. It's so fast that it's almost instantaneous, but it might not be instantaneous. In some cases, that process takes longer, right? And one of the labs that I hope we can do here would be to use this process where we can use the daughter that has a 2-minute decay, a half-life, to go to the stable daughter. So that would be the gamma, right? So the positron emission, right, that I mentioned a minute ago, where is the positron in the nuclei? When we said before that the nucleus have protons and neutrons, well, what we now know is that is a very simple idea. The protons themselves are made of space, right? So the proton somehow can get rid of the positive charge, keeping the mass, So whatever proton is retaining, it will become a neutron, right? So you have the new atom will have just less protons. From 6 it went to 5, but the same mass because the mass is protons plus neutrons. Yes.
Right. Don't neutrons have a little more mass than a proton?
Well, you could have little more mass.
Yeah.
I don't remember. We have a table at the
Yeah,
end of the
they're-
chapter.
They're
They're very
slightly
close.
different. They're slightly different.
Yeah, very small difference.
Because the electron that's in the more.
Proton, I believe, weighs
Let,
slightly more.
let me answer one quick. Yes, Kelly.
I guess my question is, there's a proton here with some amount of mass. It emits a positron, and the positron will have mass too, right?
Very little.
Very, very tiny
Yeah,
mass.
yeah.
But then it becomes a neutron, which I believe has more mass than a proton.
Oh, yes. No, but it doesn't work that way. No, because yeah. Remember what I said about it's like this, right? So when you measure, and remember, that's one question I want to ask about what happened to the Scientific American magazine. So I think I better stop now so we have time for a conversation. But that's a very good question. Yeah, but don't worry right now about finding that. That's probably a thing to do for the future, right? Right now, you can say that they are both about the same mass, the proton and the neutron. One is positive, one is not. If you get rid of the positive charge without losing the mass, then the proton becomes a neutron. And that's where we are right now. And so I'm just going to stop right now. And I'm going to, what happened to I want to stop the thing here. Where is that? Here, stop.